Okay, so you can unmute yourself, okay, and if you have any doubt, you can raise your question, because this is revision class, and I think you have understood, but still if you have not understood, you let me know. We will clarify those doubts. Okay, did you understand? Hello, am I audible to you? Hello.
Yes, sir.
Okay.
Audible, sir.
Okay, so we start with this UV visible spectroscopy. Spectroscopy, as we have discussed, it is the branch of science that deals with the study of interaction of matter with light. So whenever there is interaction of light, interaction of light means interaction of electromagnetic radiation with matter. And when this matter absorbs this electromagnetic radiation, what happens? What kind of interaction the matter has with the light? Okay, so this study is known as spectroscopy. Okay, and this reveals the about the type of matter which we are studying. Okay, the type of matter we under study. Okay. Okay. It is a branch of science that deals with the study of interaction of electromagnetic radiation with matter. Okay. I hope you have understood. So, okay. Electromagnetic radiation, we have already discussed electromagnetic radiation. Okay. You should know. Okay. Electromagnetic radiation consists of discrete packages of energy which are called as photons. A photon consists of an oscillating electric field and an oscillating magnetic field. So electric field as well as magnetic field both are perpendicular to the direction of propagation. Electric field is perpendicular to magnetic field, and both are perpendicular to this direction of the source. Electromagnetic radiation, in this we have frequency. It is defined as the number of times electric field radiation oscillates in 1 second. The unit is hertz. Wavelength, lambda. It is the distance between two nearest parts of the wave in the same phase, such as the distance between two nearest crest or troughs. These two wavelength, two nearest crests or two nearest troughs. Okay. Now, what is the relationship? C is equal to nu lambda, and E is equal to h nu, or is equal to h c upon lambda. This is electromagnetic spectrum. We are only concerned with UV visible and IR. UV visible and IR. See, in this is UV visible region from 400 to 700 nanometers, and this is visible wavelength. And UV it is around from 200 to 400 nanometers. 200 to 400 nanometers. Okay, or sometimes it is 10 to 400 nanometers. This UV visible spectroscopy. Visible range, UV range. Sorry, ultraviolet range. This is visible range. Okay. So these are the electromagnetic radiation and visible range. The wavelength of this visible range: violet 400 to 420 nanometers, indigo 420 to 440 nanometers, blue 440 to 490 nanometers, green 490 to 570 nanometers, yellow 570 to 589 nanometers, 585 nanometers, orange 585 to 620 nanometers, red 620 to 780 nanometers. This we should know, but it is not. We are not concerned with. This is not will not be asked in examination. But we should know. The principle is spectroscopy. This UV visible spectroscopy mainly. The principle is based on the measurement of a spectrum of a sample containing atoms or molecules. Maybe atoms, molecules, or ions. The spectrum is a graph of intensity of absorbed or emitted radiation. Intensity of absorbed or emitted radiation by sample versus frequency or wavelength. Show you this is graph, this is lambda, and this is absorbance or transmittance T. Absorbance or transmittance T. Okay. Absorbance or transmittance T. So spectrometer is an instrument designed to measure the spectrum of a absorbance spectroscopy. What is absorbance spectroscopy? Analytical which is concerned with the measurement of absorption of electromagnetic radiation. We already know that UV visible, UV ultraviolet 185 to 400 nanometer and visible 400 to 800 nanometer. So this is total UV visible spectrum 180 to 800 nanometer or 750 nanometer sometimes. Okay. And IR spectroscopy 0.76 to 15 micrometer. Emission spectroscopy is not there in our syllabus, so we will just not discuss. Now, the interaction of electromagnetic radiation with matter. What kind of interaction it has? Electronic energy levels. Electronic energy levels. At room temperature, the molecules are in the lowest energy levels, E naught. When this, when the molecules absorb ultraviolet or UV visible light from electromagnetic radiation, one of the outermost bond or lone pair electron is promoted to higher energy states, such as E1, E2, or etc. up to En. This is called as electronic transition. The difference we know delta E is equal to H E the final and minus E the initial. Now, then we have vibration energy levels. These levels are less these are less energy level than electronic energy level. The spacing between energy levels are relatively small, very small. For example, when IR radiation is absorbed, molecules are excited from one vibration level to another vibration level with higher amplitude. We have discussed this in IR spectroscopy. Uh, Vibrational energy levels and rotational energy levels. Rotational energy levels are even lesser than vibrational energy levels. Rotational energy levels. These energy levels are quantized and discrete. The spacing between energy levels are even smaller than vibrational energy levels. So rotational energy levels, they are lesser than vibrational energy levels, and these are lesser than the electronic energy levels. Okay. Lambert's law, Beer-Lambert's law, we in there are two topics, two terms which we have to remember as far as examination is concerned, but they will not ask derive Beer-Lambert's law. This is for our understanding. Okay, what is Beer-Lambert's law? Okay, only two terms are there: absorbance and transmittance. These two terms we should know, we should remember. They may be asked for 3 marks. They define absorbance and transmittance because last semester it was asked. Okay, so this is Lambert's law. When a monochromatic radiation is passed through a solution, the decrease in the intensity of radiation with thickness of the solution is directly proportional to the intensity of the incident light. Okay, already we have discussed the derivation. Okay, let I be the intensity of incident radiation and x be the thickness of the solution. Then this is incident light and this is transmitted light. Intensity of incident light and this is intensity of transmitted light, and this is the thickness, and this is sample, and this sample holder is known as cuvette, and the length of the sample is L. Okay, so according to Lambert's law, minus di by dx is directly proportional to I. So minus di by dx, we can this proportionality we can remove with using this k. Then we can integrate using limits, and we'll get this log natural log I by I naught is equal to minus kl. Then we can remove this natural logarithm, and this we get this term. Absorbance is this molar absorption coefficient into length of the sample holder. Okay. So this is Lambert's law. Then we come to Beer's law. When a monochromatic radiation is passed through a solution, The decrease in the intensity of radiation with thickness of the solution is directly proportional to the intensity of incident light as well as concentration of the solution. Here, concentration of solution is also there. Okay, directly proportional to the intensity of incident light as well as concentration of the solution. So two terms are there. Okay, so let I be the intensity of incident radiation and X be the thickness of the solution and C be the concentration of the solution, then minus di by dx is proportional to C into I. C is concentration, I is the incident. Okay, intensity of light. So minus di by dx is equal to K prime Ci. Integrating, we get this equation. Then solving, we get this equation. Solving, we get this equation. This is Beer's law. Okay. Absorption, this is equal to this epsilon in dot concentration dot length. Okay. This is for our understanding. It will not come in examination. There is no derivation, no, it will not come. But only we have to understand two terms: absorbance, what is absorbance, and what is transmittance T. Okay. So, so we are concerned with this transmittance and absorbance. So T is I and I naught. Ratio of transmitted intensity of transmitted light to the intensity of incident light. This is transmittance. Okay, where I is the intensity of light after it has gone through the sample, and I naught is the initial light intensity. And absorbance is related to percentage transmittance, A is equal to minus log T. This is the relation between absorbance and transmittance. Okay, so these two terms you have to remember, because for as far as examination is concerned. Now, principle of UV visible spectroscopy. The UV radiation region extends from 10 nanometer to 400 nanometer. This is UV, 10 to 400 nanometer, and the visible radiation region extends from 400 to 800 nanometer. Okay. So this is near UV region is 200 to 400 nanometer, and far UV region is below 200 nanometer. This we have already discussed. Far UV spectroscopy is studied under vacuum conditions. We are not concerned with this. Okay. The common solvent used for preparing sample to be analyzed is either ethyl alcohol or hexane. Ethyl alcohol or hexane. Okay. Now, this is very important. Electronic transitions. Electronic transitions are very important. This topic for 5 marks. Remember, for 5 marks, this topic is very important. Okay. Now, these are the possible electronic transitions which can take place in UV visible spectroscopy. This sigma, sigma to sigma star, then sigma to pi star, sigma to pi star. This sigma to sigma star and sigma to pi star. Then we have pi to pi star and pi to sigma star and pi to pi star. This is pi to this sigma star and pi to this pi star. Then from non-bonding, this we have this from here. You can see here this from this non-bonding to sigma star, non-bonding to sigma star, and then non-bonding to pi star, non-bonding to sigma star and non-bonding to pi star. We'll discuss this. See, sigma to sigma star transitions, pi to pi star transitions, non-bonding to sigma star transitions, non-bonding to pi star transitions, sigma to pi star transitions, and pi to sigma star transitions. 6 types of transitions are there. Out of these 6 types of transitions, few are forbidden. Okay. See, sigma to sigma star transitions. We have to remember this with an example. Sigma electrons from orbital is excited to corresponding anti-bonding sigma star orbital. In this case, sigma electrons they get excited to sigma anti-bonding orbitals. The energy required is very large. For this transition, the energy is very large. For example, in methane, this carbon hydrogen bond only and can undergo sigma to sigma star transitions because only sigma electrons are present. Okay, and show absorbance maximum at 125 nanometer. Absorbance maximum at 125 nanometer. So this is here lambda, lambda maximum. This is 125 nanometer. This is absorbance or transmittance. Okay. Next, pi to pi star transitions. So pi electrons in a bonding orbital is excited to corresponding anti-bonding pi star orbital. So there must be in the molecule there must be a pi electron. Okay. This compounds containing multiple bonds like alkenes, alkynes, carbonyl, nitriles, aromatic compounds, etc. They can undergo pi to pi star transitions. They can undergo pi to pi star transitions. For example, alkenes generally absorb in the region 170 to 205 nanometer. Non-bonding to sigma star transitions. Non-bonding to sigma star transitions. Saturated compounds containing atoms with lone pair of electrons. Saturated compounds, remember? Saturated compounds containing atoms with lone pair of electrons like oxygen, nitrogen, sulfur, and halogens are capable of non-bonding to sigma star transitions. These transitions usually require less energy than sigma to sigma star transitions. The number of organic functional groups with non-bonding to sigma star peaks in UV region is small, 150 to 250 nanometer. So the range is 150 to 250 nanometer. In this region, they show, they absorb. Non-bonding to pi star transitions. Non-bonding to pi star transitions. So an electron from non-bonding orbital is promoted to anti-bonding pi star orbital. Compounds containing double bond involving heteroatoms. This heteroatoms, they show this type of transitions. Non-bonding to pi star transitions require minimum energy and show absorption at longer wavelength, around 300 nanometer. Around 300 nanometer. Okay. Now, these two transitions, sigma to pi star transitions and pi to sigma star transitions. These are mostly forbidden transitions. These electronic transitions are forbidden transitions and are only theoretically possible, not possible. Thus, non-bonding to pi star transitions and pi to pi star electronic transitions show absorption in region above 200 nanometer, which is accessible to UV visible spectrophotometer. The UV spectrum is of only a few broad of absorption. So this you have to remember, these electronic transitions. Now the terms which are used in UV visible spectroscopy, They may be asked for 2 marks or 3 marks. We have already discussed chromophores. The part of a molecule responsible for imparting color are called chromophores. Okay, these are different chromophores. Okay, so what happens? What do these chromophores do? You can see here. Non-conjugated alkenes show an intense absorption below 200 nanometer. Non-conjugated alkenes, and are therefore inaccessible to UV visible spectrophotometer. But non-conjugated carbonyl group compounds give a weak absorption band in the 200 to 300 nanometer region. See how? See this chromophore. The acetone, which has a lambda maximum 279 nanometer, and the cyclohexane has lambda maximum 291 nanometer because of this chromophoric group. Because of this chromophoric group, okay. So this the lambda maximum changes. Okay. When double bonds are conjugated in a compound, lambda maximum is shifted to longer wavelength. When double bonds are conjugated in a compound, lambda maximum is shifted to longer wavelengths. For example, you can see here in this, there is no conjugation. Lambda maximum is 178 nanometer. But in this case, there is conjugation. This conjugation, and the lambda maximum shifts to longer wavelength, 227 nanometer, because of this chromophoric group. Okay. Few more things. See, conjugation of carbon-carbon and carbonyl group shifts the lambda maximum of both groups to longer wavelength. For example, this ethylene lambda maximum is 171 nanometer, but acetone lambda maximum is 279 nanometer. Ethylene, okay, and this one, you can see here the difference because of this chromophores. Oxochromes, the functional groups attached to a chromophore. Oxochromes, the functional groups attached to a chromophore which modifies the ability of the chromophore. These oxochromes, they modify the ability of chromophores to absorb light, altering the wavelength or intensity of absorption. They can alter the wavelength or intensity of absorption. Okay. See some oxochromes. See here. See, for example, benzene lambda maximum is just 255 nanometer. Okay. But phenol lambda maximum 279. This is oxochrome connected to this chromophore. Similarly, aniline lambda maximum is 280 nanometer. Lambda maximum is shifted to longer wavelength. In this case, in benzene, because of these oxochromes. Absorption and intensity shifts. This bathochromic shift, hypsochromic shift, hyperchromic shift, and hypochromic effect. First, bathochromic shift or red shift. When a absorption maximum lambda max of a compound shifts to longer wavelength, it is known as bathochromic shift or red shift. So suppose this is here. We suppose one compound absorbs here, but if it shifts some because of oxochrome or chromophore, its lambda maximum shifts to right side. Okay, so it is known as bathochromic shift or red shift. The effect is due to presence of an oxochrome or by the change of solvent, because of the presence of oxochrome or by the change of the solvent. For example, an oxochrome group like OH or this oxymethyl group causes absorption of compound at longer wavelength. See here. This is one example of bathochromic shift. See, in alkaline medium, this paranitrophenol lambda maximum is 255 nanometer, but, but I mean paranitrophenol lambda maximum is 255 nanometer, but in alkaline medium, lambda maximum is shifted to longer wavelength, 265 nanometer. So it shows a bathochromic shift or red shift because of the change in solvent. Now hypsochromic shift or blue shift, downwards, left side. When absorption maxima, lambda maximum of a compound shifts to shorter wavelength, it is known as hypsochromic shift or blue shift. The effect is due to the presence of an group causes removal of conjugation, because something is present which removes the conjugation from the molecule, or by the change in solvent. Okay, let's see here. See here again in aniline, lambda maximum is 280 nanometer, but in acidic medium, lambda maximum shifts to shorter wavelength, 265 nanometer. Okay, because the conjugation is removed. Here there is conjugation, but there is no conjugation. So there is loss of conjugation, and which shifts its absorption ability to shorter wavelength. Okay? So lambda maximum becomes 265 nanometer. So it is known as blue shift or hypsochromic shift. Hyperchromic effect, when absorption intensity, molar extinction coefficient of a compound is increased. Okay, it is known as hyperchromic effect or hyperchromic shift. See, if oxochrome introduced to the compound, the intensity of absorption increases. See, simply this is pyridine, but because of this introduction of oxochrome, the lambda maximum becomes 260 nanometer, 2-methyl, and intensity increases. Not only this, lambda maximum intensity increases. Okay, this molar extinction coefficient increases. See, hypochromic effect, when absorption intensity or molar extinction coefficient of a compound is decreased, it is known as hyperchromic effect. You see here, see naphthalene, this molar extinction coefficient is 19,000, but in this case 2-methyl naphthalene, it is 10,250. So okay, you can see here next. This is blue shift, this is red shift, this is a hyperchromic. This absorption molar extinction coefficient increases, it is known as hyperchromic shift, and if it decreases, it is known as hypochromic shift. Okay. Applications of UV visible spectroscopy, we have already discussed applications, qualitative applications and quantitative applications. Okay. Uh, it is not there in this slide, so we'll skip. Already we have discussed qualitative and quantitative analysis used for characterizing aromatic compounds and conjugated olefins. It can be used to find out molar concentrations of the solute under study. Detection of impurities. It can be used for detection of impurities in any compound. It is one of the important methods to detect impurities in organic solvents. It can be used for the detection of isomers. It can be used for the determination of molecular weight using Beer's law. Okay. These are some applications. Then the selection rules. Okay. Hello. Till now, if you have any doubt, you can ask. Hello. 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 Hello.
Yes, sir. Yes, sir.
21
Yes,
students
sir.
were there. Only now only 17 students, 16 are there. Okay, selection rule. We'll discuss. Already we have discussed selection rule. Okay. In this first is Laporte rule. So according to Laporte selection rule, Otto Laporte, it was given by Otto Laporte. According to Laporte selection rule, only allowed transitions are those occurring with a change in parity. There must be a change in parity. Okay, this is one factor. The other factor, there must be a change in azimuthal quantum number or angular quantum number by +1 or -1, by +1 or -1. So this is second factor. Okay. So the Laporte selection rule reflects the fact that for light to interact with a molecule and be absorbed, there should be a change in dipole moment. This is for IR spectroscopy, this one. Okay. We can see here Laporte meaning of the Laporte rule. Laporte allowed transitions are those which occur between gerad to gerad or ungerad to ungerad orbitals. Laporte forbidden transitions, which are forbidden. Gerad to gerad is forbidden and ungerad to ungerad forbidden. What this is the meaning of gerad and ungerad. Gerad, symmetric with respect to center of inversion. Symmetric with respect to center of inversion, such as atomic or molecular orbitals with center of symmetry. Okay, or number of nodal planes 0, 2, or 4 even numbers. Ungerad, anti-symmetric with respect to center of inversion, such or atomic or molecular orbitals without center of symmetry. Atomic or molecular orbitals without center of symmetry, they are ungerad. And what are gerad? Atomic or molecular orbitals with center of symmetry. They are known as gerad. Okay. Already we have discussed this Laporte selection rule. There must be change in parity. Okay. Now also change in azimuthal quantum number by +1 or -1. Okay. Now the other one, spin selection rule. There must be no change in, according to spin selection rule. Spin selection rule states that transitions that involves a change in spin multiplicity as compared to ground state are forbidden. So if there is a change in spin multiplicity, okay, after transition, it is not allowed. It is not allowed. Okay, it is forbidden. If there is a change in after absorption, if there is change in spin multiplicity, okay, according to this rule, any transition for which delta S is 0 is allowed. If delta after absorption delta is 0, it is allowed. You can see here delta is after absorption, delta S is 0, so this transition is allowed. Okay. If delta S is not 0, here we can see here, if delta S is not 0, change in spin multiplicity after transition, then it is forbidden. Transition is not allowed. Okay. You can see here, this is ground state and this is excited state after absorption of light. So delta S is not equal to 0. So this type of transition is forbidden. This type of transition is not allowed in UV visible spectroscopy. So these are few selection rules in UV visible spectroscopy. Okay. So this is over. Revision is over for this topic. If you have any doubt, you can ask. I'll tell you which questions will come. Explain electronic transitions in UV visible spectroscopy.
Sir,
Define absorption and transmittance. Hello, tell
sir,
me.
can you send the notes, sir?
This I have sent you just recently. I have sent you just half an hour ago. I sent you this PPT
Okay, sir.
in your group. IR also I'll send. Okay.
Okay,
Hello.
sir.
Now the questions which may be asked. Explain selection rule in UV visible spectroscopy. Explain principle of UV visible spectroscopy. These are the questions which may be asked. Okay. Explain electronic transition in UV visible spectroscopy. This is very important. Electronic transition in UV visible spectroscopy. Selection rule is important. Okay. Applications of UV visible spectroscopy. In Zoom class, previous Zoom class, I have explained you applications of UV visible spectroscopy. I'll send you a link. You can go through that those applications. Qualitative and quantitative. So they last year I think they asked qualitative. Explain qualitative application. So they may ask qualitative or quantitative both. Okay. So you should know what are qualitative applications and what are quantitative applications. Now, any other doubt you have? If you have, hello, hello, hello.
Yes, sir.
If you have any other doubt, you can ask. Hello.